get back to the coding stuff. Ooh. All right. Because I didn't see that it was working all the time. Это так странно, непонятно вообще, как это работает. Короче, okay. So we have the shaders working. We have everything set up. So the first thing I would like to do, I would like to change, well, the colors obviously, and then I would change the plane geometry to sphere buffer geometry. Three.js had the sphere buffer geometry. This object that already has some stuff. Well, just write something, guys. I'm not sure. I'm still not sure it's working all right. So this geometry, just an easy way to set up object in 3D with a bunch of detailizations, options. Let's go. So instead of plane geometry, I will just put up a new sphere buffer geometry. Let's see how it looks like. Yeah, it's a real big one. Yeah. All right. Thank you. I'll make smaller radius, so it's sphere. Even though it's not that obvious, but it's still a sphere. I can put a wireframe through thing, and we'll see that it's real sphere. All right. The next thing I would like to do, I can actually change the geometry and the colors of the sphere with just the shaders. I don't need to use any of the JavaScript anymore, just the shaders. So let's start with some Perlin noise. Well, thank you, Martin Bao. I need to find the GLSL noise function. Actually, a nice gist with all of those functions, and which one I like to use. There was some with n dots. Yeah, this one probably. Simplex 3D noise. I think it's a bit faster than the Perlin noise, and I don't really need the natural look of the Perlin noise, so I can use the simplex noise instead. So I'll head to the vertex. I don't need all this stuff. So there's nothing actually happening in the vertex shader in the main function. It's just the only line that you need to work it at all. So I'll just insert this function here, and this function is just computing simplex noise. Then what I want to do next, I want to calculate their what I would like to calculate. I want to calculate the simplex noise for each position on the sphere. So I have the position variable, and I can make a noise variable, which is going to be equal to what? To noise function, obviously, from the position. And to see this noise function, I actually can't see it in the vertex shader, so I need to set up variant called the color. Let it be the color. I need to copy it here. It needs to be vec 3, obviously, not vec 4. And I'm gonna just do the color equals vec 3 noise. All right, and here then I can use this noise, this vcolor, I mean, variant in a fragment shader to colorize my sphere. So let's see how it looks like. It doesn't look like anything at all because I have no match never loaded function found because what? Because why? Noise position, and it's noise. Okay, so it does work in a way, but we need to remove the wireframe truth part now. Yeah, so it does compute this simplex noise, so it looks like this. You might actually see how you can use it to generate some random planets in the space with the oceans and the ground parts. All right. Okay, so by changing the scale of position, I can change how it looks like. Let's divide it by 10 and see how it looks like. Well, I should probably multiply it by 10. That's how you develop the things. Yeah, this is how the parallel noise start to look like. It's a bit not always real smooth, but I think it's gonna be good enough to me. That's probably because I have way too less of the vertices on my screen. I could just make the sphere more detailed, like 62, for example. It's gonna look a bit better than that. Well, not much better, but still better. Maybe not 10 here, but just like something like 5 should be good. All right, so for now it's good. So what I really want to do, I want to use this variable now to distort my sphere. And to distort it, I could actually, what, is my stream still working? All right, yeah. I don't have it on my other screen. Fuck, okay. Okay, so I'm gonna just see the chat on this screen. Nebula noise. What do we mean by nebula noise? What exactly is a nebula noise? All right, so if I add here a time, I also have time running the whole time here. Like, I have a uniforms updated at each frame, which uses the time. I will see it living its life. I should probably divide time by 10 because it's way too fast. And it's already some nice stuff happening here. But we're on our way to do the real stuff. All right. So I actually need this noise to distort the sphere, not to colorize it. To distort sphere with this kind of noise, I would just need to change position. So instead of rendering this position, I would need to come up with a new position, like 3 new position equals something where I would distort the position. I think if I have a sphere, distorting a sphere is just multiplying each of the vertices coordinates by some number. Let's do this. First position multiplied by sine of time, sine of time divided by 10. I don't know. So it should be pulsating now, but it's not because I haven't replaced position with new position yet. Yeah, so now we're gonna see the sine gonna get bigger, and then it's gonna get smaller, and then it's gonna do this for eternity. Hello Julian. I'm good, almost good. Some course about Three.js. I think there's this Three.js book. It's a real nice one, like a Three.js book. Discovers Three.js. Yeah, just use it. It's a real nice book. Nebula animation. Let's see what do you mean now? Nebula animation like this. Yeah, we can use it. It's a different thing to do. Let's start with this one. Well, you can maybe try to replicate it with noise as well, but it's usually done with a lot of particles. So the next thing to do, I'm gonna distort the sphere, but I want to distort the sphere with my noise function. So what I want to do, I actually want to have the minimum radius for my sphere. Maybe I should just start by multiplying by noise, and let's see how it looks like. Let's see. See, it's already a cool thing to do, right? Well, the colors are a bit weird for now, but otherwise it's quite good. All right. Next thing to do is to have the minimum radius for the sphere. Right now it's just getting until the like 0 radius. So I'm gonna just do like 0.5 here, and it's gonna look much better now. See, because I'm coloring the upper parts with the noise function, like if noise is equals 1, it's gonna be white. If noise equals 0, it's gonna be black. We see black down here. And by black, I mean you can see nothing there. So it's like going somewhere deep into the blackness, like a black hole. So it already starts to look good. Well, today we're recreating this animation. All right, so I think I need to slow down the time a bit more here. Well, we can play with those variables a lot. Maybe 10 here. Maybe just 1. Yeah, by 1 you would see something like this. I think 10 was good. Okay. Next thing, let's set up the nice colors here. So the colors that you see here are actually, well, if you are into graphics, they should remind you about HSL kind of colors. Because the color gradient done with HSL usually goes like it's somewhere here, the gradient between the red and the yellow, and like here. This is a gradient on HSL scale. You can't really do this gradient with the RGB values because it's complicated to do the math between those two colors. Or maybe you could just actually use two colors and just mix them. But in this case, we actually did the real HSL colors. So I'm gonna just use the same function that the Grant used. The function just converts the HSV or HSL color into the RGB space. So I can use the HSL gradient and convert it to the RGB values, which I can use then later in my fragment shader. So I'm going to run this function, and I need to set the vec3 object here, which is going to be an HSL color. So let's just go ahead, and usually the second and the third variable, when you create a nice gradients with the HSL colors, the second and the saturation and lightness are usually static, and you just change the hue. Okay, so I don't know, the same values, and then I'm going to use noise right here. So I'm not going to use noise on the RGB scale like I did before, but I'm going to use it on the HSL or HSV scale. So it's going to be noise. Let's just see if it's just noise. Let's see what we'll get now. So it looks nice, but I think it's the gradient is too big of a gradient. Yeah, now it starts to look better. Yeah, we're getting there. I think the correct number was somewhere here. I think I also would need to add the black background because it doesn't look good on the white one. Actually, everything looks good on the black background, except black objects, maybe. So there you go, now we almost have it. Not yet there, but we get in there. I think I would need to make my sphere more detailed also to look at more smooth. Yeah, like that, maybe a bit further with the camera. A bit more further. Okay, so it starts to look better, but not yet there. We get this nice feeling. I think I would also need the anti-alias, so it looks better. Not sure if you will even see it on your screen, but it looks better now. So we are on our way. No, it's still the old macOS. Which one do I use? Mojave, because I don't have space on my HDD to update. All right, next thing to do. All right, maybe I will do a Russian speaking stream too. Okay, next thing to do. This thing on the Grant website actually has some lightning. And, well, you could replicate this kind of lightning actually with a lot of ways, but I'll just try to do it real fast with the fragment shader. I also need to use a normal the color, the normal, and I'm gonna just do the normal equals normal here. The normal to the fragment shader. I could even visualize it. Let's see how it looks like. Yeah, it looks like the normals. It's actually, I don't know, I like the normal coloring. When you color anything with the normals, it actually looks beautiful to me. All right, so we have this normal. To set up the easiest lightning, we just do light equals vec3 0, and then light plus something here. It's gonna be a dot product. Equals vec3 somewhere in the 3D space. It's actually not normalized. So light direction multiplied by v normal. Well, let's see how it looks like. What's a better way to see it? It's just do this. Oh no, maybe it's light is already vec3. I could just do this probably. Yeah, and now we see the coloring. Like the light source is somewhere on the right diagonally, and we can see the lightning working. We can do 0 here to see that it actually works, to change the color. Now we can use those variables to just color our object brighter on the top and darker on the bottom. I think you could even, in this case, you wouldn't even get the difference if it was like it's just the gradient from top to bottom. But anyway, so in the fragment shader now we have this V color, which tells us which color is where exactly. And then we have the lightning, and we need to combine the lightning into this V color. And how do you do that? Grant actually used a hemisphere lightning, so-called hemisphere lightning. So just go ahead. The formula for the hemisphere lightning are like kinda same, but a bit different. I'm just gonna take this color. It's gonna be the sky color. Yes. I'm gonna take the darkest color at the bottom, the object, like this. It's gonna be the ground color. So object is lighted from both locations, both directions. Like so it gets the top color from the how do you call it? From the sky, and the bottom color from the ground. Well, I can actually even, maybe I can use a simplified formula, and I'm just gonna do like the light equals mix between sky color, ground color, and this dot product. Let's see how it works out. Yeah, so it kind of looks like what we need to do, but if we multiply it by the color we already have, gonna get this. It's actually already almost the thing that we need to do. We just need to guess the correct direction now, probably, which is gonna be which directions be direction, light direction, maybe -1. Yeah, so it's getting darker on the bottom, it's bright on the top. We kind of getting the feel of this object right now. I think it looks pretty the same now, right? Does it look good to you? It's actually the part I like the most is you can actually just change the scale of the noise right now. I can the vertex shader go and change the scale of the noise. And what was the scale of the noise? It was 10. and you can just do double and you'll get this. It's already nice. All right, you can do 100 and it's gonna be crazy, something crazy, getting more spiky. Okay, let's leave it like that. Maybe 7. Yeah, I think it's a bit better, like, more smooth now. I have Twitter. You can just write me on Twitter. I think there are DMs on Twitter, so you can speak there. All right. So the next part. Let's go for the next part. We have those dots orbiting the sphere and like doing all those wavy things. Let's do the dots. I already have the vertex particles shader here. It doesn't do anything. It's just the basic particle shader that I just stole from the Three.js examples. I'm gonna also create the how do you call it? Fragment particles GLSL. And I'm gonna copy paste it here. For now, I'm gonna just use the GL. Let them be red. Just delete all the stuff. I don't need all this shit. Maybe just a texture. And I would need to create the points. Three.js has already an object for the points. Three.js points. So let's get those points. Two points. Where the fuck are examples of points? It doesn't matter which example I'm using. I'm just gonna show you how you create the points. So it's gonna be just particles and then scene add particles. All right, it's the same way as you create all the other objects. Let's do this. So I have add objects. I'll have also add particles. I'm gonna copy paste the previous code, but particle geometry, particle material, and it's gonna be points. I'm gonna rename the material to particle material, and it's gonna be vertex fragment particles. And I would need to include them as well. Yeah, that's it. Should be working now, or at least getting me some error messages. Cannot read property uniforms of undefined because this material, probably I messed up the variable name because because I didn't add the material part here at all. And this should be still just the material. Hope it's all understood that I'm doing. I'm just adding another object on my Three.js scene, and it's gonna be particles, so it should be working, kind of. I don't get any errors, but I guess the particles are so big that I just don't see anything. That's because in the vertex I multiplied the size by 1000. Why do I see the red? Did I change something here? Fragment part. Oh, because I changed the shaders for the object. So they use the wrong shaders now. This material doesn't need those particles. Let's see. Yeah, so we get this. It's actually another nice animation that you can do with the shaders. See how it looks like if you combine some nice looking colors. I bet it's gonna look awesome. So let's go ahead. I'm still creating a mesh here, which is a sphere buffer geometry, and I need to create points. So what it will do, it actually will create the points for me in the shape of the sphere. Easy as that. I could make the radius a bit bigger than that. So now my object is contained in those points, but it's not the points that I need. You see, those points are shaped in the concentric circles and they're boring as fuck. And if you check these points, they're not as boring. These are the cool points, and those points are boring. This distribution of the points, it has a lot of like ways to be done. And one of the two most famous ways, I'm just gonna go ahead and show you. Not this one. So there are the disco ball distribution, the golden sector distribution, and Saf and Kuijlars. I'm sorry for this guy, I don't know how to pronounce it. So this weird name. And this is the ways to distribute points on a sphere, to uniformly distribute points on a sphere. And the one that I'm going to be using today is the golden ratio distribution, because I think it's the easiest one. This one is also an easy one and I like it. Maybe I will use it in some further animations. These both look cool because they're not that boring like the disco ball. Like the disco ball is too predictable. You can see all the lines of the disco ball. You can see all the lines here as well, like the circular patterns. But at the golden ratio, you can see it. So to use the distributions, there are already some algorithms to do this kind of thing. And there's a 2006 article to do exactly what I'm intending to do. By the way, yeah, 90s. What have you been doing, guys, in 2006? I'm gonna be using the information from 2006 now. So there is an algorithm to distribute points on a sphere, and let's go ahead and use it. So first of all, I think I would need to change the way that I create those points. First of all, I'll create some n, which is going to be 1000, like I need 1000 points. And then I'm going to just copy paste from some of the examples, buffer geometry. Let particle geometry equals buffer geometry. I'm gonna ditch the sphere. So now it's empty geometry. Nothing have been done before. I'm gonna use the array. I'm gonna create positions, and it's just 10. So I need to create 1000 points. Then I would need to get a loop until n, and inside of this loop I'm gonna just do positions 3 multiplied by I, because I need to have 3 coordinates for each of the vertices, because we are in the 3D space. And let's make it math random for now. +1, +2. And then I need to attach this position to this geometry, done with the set attribute function. Just not to type it again. Okay, so I'm gonna do this particle geometry, set attribute position, like a new buffer attribute. Positions 3 means that I have 3 values for each of the vertex. And well, that's it. Probably should see now the randomized points. Yeah, I see them because the math random goes from 0 to 1. I see them in one of the squares. Well, the usual thing to do is to multiply it by 2 and -1, and you'll see it's randomly distributed of the sphere. But what I need to do, I need to use this algorithm for the distribution of my points. So let's use this algorithm now. This is a pseudocode. I don't know which language is that. Is it Python or something like that? Probably. So I need to set up an increment before my loop, let increment equals math p. This is actually the golden ratio part. 3 minus math sqrt 5. Then I need to set up some offset equals 2 divided by n, which is the number of my particles. Again, this is the same points on the sphere n. All right, and inside the loop, inside of the loop, I will calculate the y coordinate, the x, and the z coordinate of each of the points. So let's do this. Let y equals, what is that? K is the increment, not the increment, but the increment on the loop, divided by 2. So we just translating the pseudocode into the JavaScript right now. The r is the angle, probably. Oh no, it's the radius of the point. Okay, in between radius. So it's gonna be sqrt from square root from the 1 minus y squared, and then I need to calculate the actual angle. It's gonna be I multiplied by increment, and well, that's it. Then I could just use, for the x coordinate, I could use this math cos p. For the y coordinate, I will just use y. For the z coordinate, I could just use this. Okay, mass sine multiplied by r, and let's see if it wouldn't be working because I have the Python code inside the JavaScript, which will never work for you. Off is not defined. Off is not defined. I called it offset. Math is not defined. I used something else is not defined. P is not defined. Let P. It's good now. Okay, so we have the sphere. You can actually already see that we have this even distribution of the points. Let's make the radius a bit more. Let's radius equals 1.5, and I'll just multiply each coordinate by the radius. So there you go, you have a uniform distribution of a sphere with a golden ratio algorithm. And it looks beautiful to me because you can look on this sphere from any direction and it looks uniformly distributed to you. Okay, it's beautiful, isn't it? Math is beautiful. All right, next thing I would like to do, I can actually use, I don't know, 6,000 points. Make it a bit more dense. I can use a bit bigger radius for me. I don't think it's actually why do I need to make a pixel perfect copy of that website? We just do something like that, yeah, right? Something that looks good to me at least. So we have those points red squared now. What next I need to do? I need to animate them. They actually have them rotating, but let's do the rotation as the last part. So the next thing that I want to do is to do those waves on the points. You see here, they are being like this all the time. So this is obviously the sine function, and I just need to use it inside my shader, which is calculating the position. So I can create the new vec3 new position equals position, probably. Maybe just call it P for short. And I'm gonna be using P here. So before that, I can change P in some way. Let's see if it's still working for me. Yeah, I can change P in some way. So I can, for example, do like Py, this is the y coordinate, the vertical coordinate of each of the points. I can do plus equal what? Plus equal what? It's going to be a sine function, but sine goes from -1 to 1. This is a bit big to me, so I can multiply it by something small. And inside of the sine, and also sine goes from -1, and I need sine to be going from 0 to 1. This is going to be from 0 to 1 now. And inside of the sine function, something from the PY probably, why not? But PY changes from -1 to 1. It's a bit too small to me. I need to make it bigger. Let's see. I think 100 was too big. Yeah, you can see the sine waves now. And to make them move, I would just need to add time, just time. Let's see how the time works. It doesn't work because I don't update this uniform for this material yet. Points material. What? Not with. Is it just? It's particle material. Yeah. Yeah. Now, so now we have those waves. It actually looks almost like what we need to do. But we can add some more distortion here. Vertex particles. We can do some z coordinate. Change it a bit. Make it a bit smaller. 10, for example. To make it more wobbly, I don't know, more wavy. But it already looks good to me. Maybe a bit smaller here. So one of the last things I want to do, I want to change the particle colors. It's a fragment particles, so I'm going to do them semi-transparent. I'm going to do them white, but they're not white on the example probably. And I need to also make the object transparent for it to work. It starts to look better. I think it's blue, some kind of blue here. Not really white. Okay, let's just use this color to make it a bit closer to the starting website. It's not the same, but maybe I should make it brighter. All right, good enough. Maybe I should make it a bit less transparent as well. And it's getting closer already. Maybe a bit more distortion. Well, it's already, I think it's already in place. It's the effect we've been looking for. The rotation as well. These points rotation y, because I'm going to be rotating for the y-axis, equals time divided by 10, for example. No? This time divided by 10. Yeah, we're getting there. I think I could also, it actually looks pretty good now. Well, of course you can do any kind of distortion for the particles, like the one we used for the sphere here. Use it for the particles as well. It looks good like this too. Like when you see the particles only at the background of this theme. And it's obviously 60 FPS for us, even though we're using a lot of particles. Let's see how many particles we can use here. Can you use the algorithm for the gold ratio for the planes too? Yes, you can. You can use it in any space, and I think you can even use it for the volumes. Yeah, you can use it, obviously. Of course, use it. I would be grateful if you will let me know, or just send me the link where you used it, just so I would be proud that I don't know, inspired something or helped to do something. Otherwise, you can use it, of course. What I wanted to do, the last thing, I wanted to see how many particles we can get there with the 60 FPS. So I'm just curious, you know. So we had 6,000, let's have 60,000, and still 60 FPS, of course. Yeah, thank you, Dmitry. Okay, I think I'll make the particles small, and that's how you actually do the nebula part. You just do lots of particles and boom, boom, boom. I wanted to make particles smaller. It's here. 10 times smaller. See how the particles look when they're small. You also get this nice edge, which is a bit lighter than all the other parts, which I like the most. So 60,000. Let's go for the 600,000 particles. It looks like the sphere almost now. But I think they're too big. Oh no, not too big. They're kind of good. This is a weird look we get here. I think it's just too much, but let's go for the 2 millions. What? Just like, oh, now we get the FPS drop, like the 40 FPS with 2 million particles. Okay, 2 million, so we can use 2 million. With the 1 million, we would probably not even get that FPS drop. Yeah, at least on my PC. I got 2 million particles. And I think the sphere geometry actually has, like, let's see the sphere by sphere geometry. How many vertices are in there actually? Right now. So we have the position attribute, and it's well, it's not too big. It's just 80,000, and I need to divide that by 3, so it's just 3,000 particles. Oh no, it's normal, but they're all the same. So just 25,000. So I can actually make my sphere a bit more detailed here. Okay, I will remove the billion particles. 10,000 is enough. Just make them a bit bigger again. It's good enough. And I made my sphere more detailed, and you see how it starts to look even better. So I can probably do the trick and make it even more detailed. Let's go for the sphere maximum detalization. And let's see how the simplex noise would look like. So it looks even cooler. It's more smooth now. And this is probably what the Grunt did. He did a more detailed sphere than I did. So now it looks just the same. So that's it. That's it for today's animation. If you have any questions, I know you're late. Yeah, but it's 11 a.m. in Kiev time, you know. And I have this countdown on my stream, so you can actually see it right there. Thank you everybody who've been with me today. I hope I will make streams more often now. It's been a tough period to me, but let's get out of it. If you have any questions, I have like 1 minute to tell you those. Otherwise we are done. The cool thing is done for the day. What is last I did? Well, last I was experimenting with some I did cursor like that. You don't see it, right? I did stuff like this. Like it's with a bit of the physics, but you could also hover all the items. Nice little thing. OJL прикольная, но ее нужно учить. Еще я с ней никогда не занимался. All those libraries are very cool, but well, none of them are universal. You just need to know your instruments, your tools, and use them wherever you can achieve something better with those. There are no silver bullets, so you need to know everything. WhatsApp, email. Okay, I have email. You can just write me on an email. I have Twitter. I also have a Patreon. And if you have enough money, you can support me there. This is my Patreon. Still have some supporters. Not much. Web GPU is a nice thing. We already can use it. I mean, there are GPU ways of computing already on the shaders, which are kind of workaround. So it's gonna be a lot simpler and easier with the web GPU. But we can't really use it for now because it's not supported everywhere. It's easier to use a pipeline with 2 shaders, ping-pong shaders, and use the computation shader. Can you create a course for front-end development with WebGL, Three.js, and all those? Yeah, I'm actually thinking about doing that. I'm just not yet sure. Well, the plan was to do a lot of English-speaking streams so I can actually do a nice English course. And by the way, if you have some front-end meetups in your city, just let me know. I would like to come to your city. I mean, in Europe, maybe. In Ukraine, I've been to all the cities now. Thank you. Thank you, guys. I'm still in contact. You can write me on Twitter, email, anywhere. It'd be nice to speak to you. Hope you like the stream. And I will see you in a week, probably, or maybe in 2 weeks. Because next week I'm in Vienna. If anybody in Vienna would like to have a beer, just let me know. Have a nice day, guys. Be happy and do what you love.